Hi everyone, and welcome to the fifth and last lecture of my course on programming synthesis and the ARC challenge. So today we're kind of coming back to the ARC challenge as such and looking at some, well, first of all, what is the ARC challenge? And then some approaches that were particularly interesting from the last edition and that got the paper prize. So reconnecting the thread back to the ARC challenge after we've basically only talked about program synthesis for a few modules now. What we have seen in the previous lecture is how to define a program space. So that was the module that introduced the problem of program synthesis. And then we had a long discussion of various ways to search this space for a program that performs well on the task, for instance, with symbolic methods or with neural network methods or neurosymbolic methods. And today, we're discussing how to apply all of this to the ARC challenge specifically. Some general information on the ARC-AGI challenge. The task data is public. It's available at this repo. There's three data sets, which you must keep distinguished in your mind. There's the public data set, which consists of 400 training tasks, which are kind of easy, and then 400 evaluation tasks, which are more difficult. And then there's the semi-private data set, which consists of 100 difficult tasks, and then a private data set, which consists of 100 difficult tasks. The semi-private dataset was introduced, I think, because people really wanted to attempt to solve ARC with systems that kind of go beyond the constraints imposed in the private dataset, and we'll talk about that more in a second. For the 2024 edition of the ARC Prize, 1,430 teams submitted with almost 18,000 entries. So it generated a huge amount of interest, probably partially because of the monetary incentive. So what do the tasks actually look like? Well, each ARC task consists of a set of example grids, and then usually one, perhaps more, tests. And each example consists of an input and an output. And basically, the input is a grid that's at max 30 by 30, and then is transformed according to some unknown rule into the corresponding output. Here you have usually three, sometimes more examples of inputs that are applied, that this rule is applied to, and then the corresponding output that's generated. And in all of the cases within a task, the same rule is applied. So you have some demonstration pairs with a median of 3, one or more test inputs, mostly one. Sometimes they want to really make sure that you got the right transformation, and so there's more than one. There's up to 10 different colors in each for each task. And the public data is encoded as a JSON, like it's shown here. So solving a task is kind of slightly more complicated than you might expect. Instead of just getting a single attempt, you get 3 attempts for each test input. And and then the score that you get depends on the fraction of solved tasks. Where a task is considered solved if at least one of your attempts gets the output correctly. The binary, so the feedback is just right, wrong. So that's the general setup of ARC, but of course you get some additional information about how you can solve, how you can approach the challenge. And so what the ARC people tell us is some information about the priors that your system should have. So the kind of concepts that should in some way be encoded, be manipulable by your system. So they make a list. It's a somewhat informal list, so it's not completely formally specified, but I guess that is the nature of the kind of concepts that are being talked about here. So you have an objectness prior, and that includes things like object cohesion, object persistent, and object influence via contact. So here you kind of you see this and you immediately think, well, this is an object, and this is an object, and this is an object. But it's not just about kind of connected regions on the grid. It also can depend on colors or other things. So sometimes you have an object which is partially occluded by a different object, and so yeah, you can have more complicated patterns for what counts as an object. Then you have persistent, where object persistence, which you can have occlusion of objects, and then objects can influence each other via contact. For instance, here you see one object that moves until it encounters a different object, and then it stops moving. Another prior is the goal directedness prior, where you can kind of see these constructions which go from one point to the other. So in this case, you have this line which keeps going until it encounters an object, then changes direction, and keeps doing this until it ends up on the object it's trying to reach. Then you have numbers and counting priors, so your system must be able to manipulate number concepts and count objects. And usually it's kind of small numbers up to more or less 10. And then you have this kind of basic geometry and topology priors. So your system should be able to understand basic geometry and topological properties of objects. Okay, so those were the priors that are given in the original paper. The competition itself happens on Kaggle. So you have a grand prize of 600,000 for the first team to reach 85% on the private evaluation set. There was a lot of confusion caused by people saying that O1 had solved the ARC challenge, but that was only about the private evaluation, O3 actually, not O1. So as things stand, yeah, this grand prize is still unclaimed. So nobody has managed yet to get to 85% on the private evaluation set. There is a slight worry about the fact that the private evaluation set has been the same since ARC was introduced, which means that the ways that the performance of different systems leaks a little bit of information about what's in the private set. And so now they are kind of creating a second version of ARC with new and different tasks. There's also 50,000 in prizes for progress on the Kaggle leaderboard, so that's the semi-private, and 75,000 in prizes for the best paper submission. And as we will see in a second, best paper doesn't just mean higher accuracy on the tasks. There's a few conditions. So you're calculating the accuracy on all the 100 private tasks. Then you have a condition on how much time your system can spend solving the tasks. So everything has to happen in under 12 hours for all of the 100 private tasks. You don't have internet access, so that's also a problem for all of these solutions that try to use LLMs. So then you also have this semi-private competition, which allows internet access and has this kind of relaxed compute constraints. That's also 100 tasks. And also you have 1,000 times more compute and up to $10,000 in API credits. This is the hardware that they've been using for the private competition, so for the actual ARC prize. So since the introduction of the challenge in 2019, the accuracy has been going up and up on the private um, um, competition. And well, it actually jumped quite a lot higher in 2024, so last year, because of the introduction of various kind of innovations. And here are some that are particularly interesting. So we have deep learning guided program synthesis. So the way that the ARC people phrase it is you can leverage deep learning models, particularly specialized called LLMs, to generate task solving programs or guide the program search process beyond blind brute force method. So that's the kind of approach that we have talked about in the last lecture and in the last module on neural search. Then you have test time training, and this applies to transductive models. We've already talked about transductive models. So fine-tuning an LLM at training time on a given ARC-AGI task specification in order to recombine the prior knowledge of the LLM into a new model adapted to the task at hand. So at test time, you kind of fine-tune the model, do something with the model, do something with the LLM. Generally speaking, you fine-tune it to get higher performance on that specific task. And then lastly, combining, so creating an ensemble of program synthesis with transductive models. So you can merge together the two approaches into a single super approach. And this relies on the fact that these two approaches tend to solve different tasks, which is one of the kind of most interesting results from last year. There's a bunch of resources for the ARC challenge. So there's an active Discord channel where people are constantly posting about kind of the latest news in ARC world and approaches, and looking for other people to approach the competition with. There's the Kaggle discussion. There's a YouTube channel with some videos. All of this is linked to in the ARC website. And then on GitHub, there's a bunch of resources. This is one that I really like. It's a really nice collection of various resources for the ARC challenge. Okay, let's get to the actual approaches. So the paper awards are assigned based on novel concepts, regardless of how the solution scored. I thought this was a really nice approach from the ARC people. And indeed, one of the very valuable things about the ARC competition, the ARC challenge, is that it has generated a lot of new ideas, not just specific to ARC, but for program synthesis in general. So it made sense that kind of highlight these original approaches and new ideas that came out of trying to solve the ARC challenge. So the first place prize, which was $50,000, went to this paper from Lee et al., last author Kevin Ellis, combining induction and transduction for abstract reasoning. And the basic idea here is that, and I think I've already shown this plot in the previous lecture, is that you have both an induction system and a transduction system. So you have a system that sees the examples, generates a Python program explicitly, and then runs the test input through the program to get the proposal, the solution, the attempted solution for that task. And then you have a transduction system that doesn't generate a Python program, but just kind of sees the training data, the examples, and then guesses directly an output for the given test input. There's a couple of kind of smart moves in this paper. One is the way that they generate new examples for training the system. So they start with 100 C problems, Um, and then they produce manually produce solutions for each of them, and that gets them to 100 seed solutions. And then they use an LLM to kind of remix them within a data kind of synthetic data augmentation strategy, and that gets them 100,000 seed problems with solutions. So the models are all neural networks. Both models are neural networks trained with meta learning. They are both fine-tuning of Llama 3.18 billion instruct. And yeah, so they get to a very large synthetic data set, just augmenting the 100 seed tasks. One really interesting observation that they make is that the performance increases with the synthetic size, but saturates with the seeds, which means that essentially, if you make 100 seeds, you've kind of all the concepts that you need to solve ARC are kind of somewhere in those seeds. But then the model needs to see them in many instances, in many different variations, to learn how to use them. And so the manually generated seeds, you don't need that many of them, because all you need is the concepts to be somewhere in those seeds. And then you need a lot of synthetic examples that illustrate how to use those concepts in various ways. The most interesting and the most important observation or result from this paper is that the tasks that are solved by the transductive model are complementary, more or less, with the tasks solved by the inductive model, which means that essentially the tasks that the inductive model solves are not solved by the transductive model and vice versa. This is kind of a pretty stable and significant result. So why is this important? This is important because it points to a very simple and quite effective strategy for solving our tasks. First, you try induction. And the nice thing about induction is that you can check on the training data, on the examples, if you got the program right. So you try this as much as you can. And then once you're running out of time, you just do transduction once. You don't know if you kind of hit the example data, if the kind of implicit program that the neural network is guessing actually fits the examples. But the fact that the system, that the inductive model didn't manage to solve it, gives an indication that maybe the transductive model can. And so you get a kind of this very nice complementarity of the two approaches, which means this is a surprisingly good strategy. Also, it's a really nice paper because at the end they have a lot of suggestions and ideas for future work. So if you're interested in developing your own solution, this is a good starting point, I think. The second place, so $20,000, went to this paper, the surprising effectiveness of test time training for abstract reasoning. And this paper focused on test time training. And the general strategy goes as follows. You start with a pre-trained model. Then you fine-tune it on the available ARC data. Okay, that makes sense. And then for each test input I, you generate new training data. So as you go at test time, you generate training data with the examples you have. So you expand this small set of examples for that task into a big set of examples. And then you fine-tune the model with this synthetically generated data set that is specific to the task that you're trying to solve. Of course, the good thing about this is that you can do it while you are solving the tasks in the private set, which means that given the constraints on time and compute, you can use the you can let the model use information that you don't have when you're constructing the model at home. And then you reset the parameters for the next input, the next task that you're trying to solve. These are the models that they use. And again, they get good performance with surprisingly small models. This is how they produce the synthetic data set given a specific task. So what they do is they do in two steps. First, they create a bunch of leave one out tasks, and this is done in a very kind of clever way. They essentially ignore the test uh, uh, case because you don't know what the solution is for that one, and then they take the test the cases, the examples for which you do have the solution, they remove one and they use that as the test grid, but now you know what the solution for that one should be. So you have this kind of leave one out task generated in this way, and then for each one of these tasks for which you know the solution, and so you can you can fine tune the network on them. You expand each one of these. You generate a bunch of other tasks given each one of these leave one out tasks by using these rule-based augmentations. And these are essentially transformations of the grids such that if you transform both the input and the output, then the transformation that solves the task is likely to generate for the transformed input the transformed output. And this isn't always true. That depends on exactly what the transformation is, but there's a kind of set of transformations which where it is quite likely that this is the case, and you can see them here. So just combinatorially with this approach, you can create a huge data set even from just a few examples of the transformation. One thing that is that comes out of the tests that they did on lesioned models is that every piece of this procedure seems to matter. So you have for instance, the fact that you are doing this fine tuning on each individual task at test time rather than on the whole data set of the tasks in the private set. And if you do it on all the tasks at once, that decreases performance. If you don't apply the transformations, that decreases performance, and so on and so forth. So they get then eventually to a kind of impressive accuracy given how simple this approach is. Then the third place for 5K went to this paper, searching latent program spaces, which is an extremely elegant, interesting idea. And the way that it works is that they, instead of dealing with explicitly constructed programs, they learn a latent encoding of the possible programs. So what they do is they have the task, then they encode the task into this kind of space of latent programs where each point on the space represents a program. And then they can take kind of the tasks and decode them into a solution. And then they can kind of move around this space until they get to a point, given the decoder, where the decoded task, the decoded grid, is what you want it to be. And then once you've trained this a bunch, you should get points in this space. The encoder should give you a point in this space that, when decoded, corresponds to a program that encodes the transformation. So the encoder maps input-output pair to a distribution in latent space. So these are kind of variational autoencoder strategy. And this is just a small transformer. And then the decoder maps an input and a latent program into a distribution of outputs. And again, it's a small transformer. And then you have this idea of the latent optimizer that starts with the encoder prediction and search for a better program. And that is done and kind of for each task, you kind of can go around this space searching for a better solution. The system is trained end-to-end on the ARC dataset. And again, they get a kind of not as high a performance as some other systems, but the approach is so interesting that it deserved a prize. Then you have the runner-ups, so the runner-up papers. And the first one is this paper, The LLM Architect Solving ARC-AGI is a Matter of Perspective. And here they have a kind of rather complicated set of steps. You start with a base model, you have the public ARC dataset, which is augmented with some of the strategies that we've kind of, strategies similar to the ones we've already talked about. Then you fine-tune the initial base model with this augmented data set. And then you have at test time, you augment the private ARC data set that gets you to the final model. Then you can do inference that gets you a set of candidate solutions, which is augmented. And then they have something that we haven't talked about yet, which is a strategy to score the candidates. And then they have a decision rule that gets them to the final prediction. So they have this kind of tailored data augmentation techniques and optimization of the data format and training performance. So they kind of squeeze some performance, squeeze some accuracy with this really kind of specific, handmade, tailored design features of the system. Then we have OmniArc by Barbadillo. The intuition here is that in order to solve ARC tasks, we should learn how to look at the data. So once we look at the data in the right way, the task becomes easier. So that means effectively that what you want to do is you want to learn a good representation of the data. And the way that the model, the LLM, can learn a good representation of the data is by not just doing kind of solving one task with this data, but rather solving a bunch of tasks, and that across them require you to have a salient, nice representation of that data. So the pipeline is Barbadillo takes this tiny Quen model, which is also the one I've been using in the lab for neurosymbolic search, and he fine-tunes it on a publicly available ARC dataset. The model was fine-tuned to do a bunch of things, like generate the outputs for test samples and learn the input distributions and generate new input. So the model does a variety of things, not just the most natural one, which is transduction. And then the model also does test time fine-tuning with the private test data, which is a strategy similar to the one we've already talked about. And this test time fine-tuning is only for the task of generating the test output, so for doing transduction. Finally, there's a step of data augmentation and voting to select the predictions. So these are some examples of the tasks that the LLM is trained to do. Example plus input to output, which is just what we've called transduction. Examples to code plus input to output, and so on and so forth. So then we have this paper by Fletcher Hill, mini-ARC, solving abstraction and reasoning puzzles with small transformer model. And the main idea here is, what if we try to use a tiny transformer and train it from scratch just on the ARC challenge data? So this is a tiny model, 67 million parameters, trained just on ARC puzzles. And the reason why this works at all is that Fletcher Hill made this really nice custom-made embedding strategy that contains the grid row, the column, the input output, so whether the point it's seeing belongs to the input or the output, and the example index, so which of the examples is it seeing. And it's trained on synthetic data. It also does test time training. So it constructs a new dataset and fine tune until it basically gets to high accuracy or runs out of time. And then it's for some of the time, the model is also trained on refinement, which means that you get the inputs and then a partial solution, and it needs to kind of refine it into the correct solution for that input. This is a plot from the paper that shows how the LLM does how the system does the encoding, and then how the LLM does the transformer model does the generation. So you get the examples, then you combine them and flatten them with this tailored encoding system. And then you run the sequence through the encoder layers, and then you get this output that you can decode and get to the actual guess that the model makes for that task. Finally, I think finally, yes, we have this paper towards efficient neurally guided program induction for ARC-AGI. This is kind of a more proof of concept than other approaches, and yet one as a runner-up, which goes to demonstrate that in kind of innovation is the point and not performance. And what it does is identifies 3 different paradigms. So you can learn the grid space. So essentially what you do there is you learn similarity between grids conditioned on a domain-specific language of the kind we've talked about in the previous modules. So the way that OLET describes it, at each iteration of the search, the algorithm attempts all possible primitives on the current intermediate grid in the program execution and selects the one that brings it the closest to the target grid state. You can also do learning on the transformation space. This is discussed only briefly. It's kind of more, more experimental. You train a model such that, given an intermediate or starting program state and a target grid, predicts the probability distribution over the DSL for the next token. And this, it explicitly feed back into each decoding step some notion on the intermediate state of the program. So then you can also learn the program space, and this is the one that most time is spent on. It's called Grid Coder. It's kind of similar to Dream Coder that we talked about in the previous module. And so what you do here is you train a transformer to output a program using a predetermined grammar, so a domain-specific language with a certain syntax that solves the task. And the transformer outputs a sequence of probabilities over tokens that can be interpreted as a probability distribution over the program space. The search algorithm enumerates the space of possible programs, and it tests the programs for correctness. I was wrong. There's one more paper. So this is a kind of 2D NGPT model for ARC price, and this was developed just in 3 weeks. This was before making this online course, I gave this course for the Master of Logic students at the University of Amsterdam, and this was a block course that lasted 1 month, and this paper was the inspiration for this course, where students could kind of develop their own, had essentially 3 weeks to develop their own solution. And I thought, well, if this paper could do it, maybe the students also can. And indeed, we got some interesting approaches from the students, and well, it was a lot of fun. So this model uses a tiny transformer, 42 million parameters, trained again from scratch. And the main innovation in this paper is that they use 2D attention, so a kind of interesting attention mechanism. It also uses the original test time training strategy. and also invertible transformations. So this is an idea similar to the ones we've seen before, where you use transformations that kind of keep the solution. So for each task, we could create, this is what Jay says, for each task, we could create another task by applying either a 2D symmetry, so rotation transpose, or a color symmetry, a permutation. There are 8 2D symmetry, depending on the task, up to 10 factorial relevant color permutations. So again, the idea here is that you have some transformations where you can massively increase the set of examples in a way that, well, they are obviously other examples of the same transformation for us, but still helps the LLM to see the kind of all the possible ways that you can use this transformation. So those are equivalent those are equivalent tasks for us, but not for the LLM. So the LLM still improves observing these transformed examples. So you have accuracy of 17% on the public evaluation dataset. So not necessarily a very high accuracy compared to the other tasks, but to other approaches. But this was impressive given that this is a really small transformer model. And then finally, honorable mention goes to Ryan Greenblatt's approach, which I think took many people by surprise. So what he did is just took GPT-4o and asked it to generate 5,000 samples on each for each task. So here, what GPT-4o is actually generating is Python programs, essentially, and Greenblatt finds a kind of very clear scaling law as a function of so it's a linear increase in accuracy given the logarithm of the number of samples that you can take from the model. I think he's also the author of this meme that appears on the page, which then I've seen loads on Blue Sky, and is kind of comparing to ethos to the ARC challenge. On the one hand, this neurosymbolic AI approach where you try to develop clever systems that manipulate the tasks and train the models in various ways. And then on the other hand, you just take a model, drum a bunch of samples, and perhaps get high accuracy. There's a couple of problems with this approach. The first one, as we have discussed, is that you can't really use it for the private set because, well, you don't have access to these big LLMs that can do this very well. So you don't have access to the internet, and you have constraints just because of the time and compute with respect to how many samples you can generate for a task. So in fact, Ryan Greenblatt's solution was not. So this accuracy is not on the private test set. Which is also why I'm mentioning it's a honorable mention because of the impact that it had on the discussion, but it's not one of the papers that were selected for a prize. So there's a bunch of recurring themes that came up in the 2024 edition of the ARC Challenge, and I think that it's worth trying to summarize them. So there's a few common successful strategies. You can use additional ARC-like datasets for fine-tuning and training. So by now, people have designed a bunch of additional datasets that take the form of ARC tasks, and you can use those to train your model or fine-tune your model. You can augment datasets with various transformations at each stage of the model. So you can do it at home on the publicly available sets. You can do it at test time on the private tasks. You can also create more tasks by using this leave on out approach. So you remove an example and then you use that as if it was a test case where you know what the solution is. You can also use voting systems to aggregate various proposals. I've only mentioned this, but I think that's one of the things that are kind of still underexplored. You have a bunch of solutions. You want to know, okay, how do I pick one if I cannot kind of test, if, for instance, if you're doing transduction and you don't know how well they fit the examples in your task. Um, and then you need to define some kind of voting procedure, some voting system that decides on one of them. There's also custom encoding systems. We've seen a couple of examples of this, and this also seems to be kind of an underexplored direction for approaches. All projects come with public code. That was one of the conditions that the ARC people, the ARC Foundation people put. So have a look in the code and see, see how what you think. Maybe it's an inspiration. You can always email the authors. I hope not too many people see this, and then the authors get a flood of emails. But yeah, that's always good. I think this is something I always tell to the students. Usually people are very friendly. If you email them, they either say that, I'm sorry, I don't have time to answer, or they'll give you something useful in return. So it's always worth a shot. Yeah, obviously play to your strengths if you're trying to develop a solution to the ARC challenge. So what do you know about that other people don't? For instance, you might be able to design a fancy logical domain-specific language. This was something that I told to the Master of Logic student in Amsterdam, or maybe a fancy voting system, who knows? So try to see what your competitive edge is. In conclusion, so the accuracy is clearly going up every year, and there were some kind of recent results with big reasoning LLMs that suggest that maybe even the ARC challenge is slowly saturating, although not in the private set. The reasoning models are promising, but again, the good ones are too large to be able to win the prize. The ARC-AGI version 2 is going to be out by the time you see this, so I'm looking forward to seeing that one. There's much more to say, pretty much for every topic that I mentioned and briefly discussed. As I said in the introduction, this was all very informal. I wasn't trying to be very precise. I probably got a few details wrong here and there when I was discussing the papers. Obviously, also, this is not my job, so I was doing this in kind of the free time I have in the middle of a kind of rather exhausting semester with teaching. But nonetheless, I hope you enjoyed it. There's going to be one lab for this module as well, so go and check that out. And yeah, as I've said in the first module, I'm very open for suggestions. So let me know what you think. There's anonymous feedback form. It's anonymous, but don't be nasty, please. I know this is the internet, but be kind. And yeah, let me know what you think. And I hope this was useful. And good luck with developing your own approach.